today I gave a bunch of different resources uh, in the Slack that I intended to review, and so let's look at them. I'm having a little trouble because this one tutorial, um, sentiment analysis with BERT and transformers by Hugging Face using PyTorch and Python. This thing I had gotten the Colab notebook to work, but today I can't seem to get it to work. So I'm not sure how we're going to handle that. There's, I guess, the first resource that I wanted to look at was the Hugging Face transformers on, just the Hugging Face website. And there's this quick tour that just gets you an idea of what you're going to be doing when you start to do a task. So we're thinking of doing the simplest kind of task, which is a classification task, and it just gives you a bunch of steps that you can do to get ready for the task. And the two things that are common that you have to worry about are you have to get one of the BERT classifiers, and you have to get an encoder from the library, from the Hugging Face transformer library. So it goes through how to do that. Actually, first he does this very quick example, just import the sort of the vanilla sentiment analysis classifier that they already have available, and then you give it a sentence, and then it tells you whether the sentence is positive or negative. So, this pre-trained model works right out of the box.
Hey, Joseph, I haven't looked at the pipelines for transformers. Is it because we're taking some raw text and then we're doing some whole lot of stuff, and that's why we need pipelines, or is there another reason?
Well, there's things you have to do with this the sentence, and there's several things. One is you have to put, if you have a bunch of sentences, you have to put a separator token in between the sentences, and then for any classifier task, you have to put a CLS token at the beginning of the sentence. And the third thing is that the sentences have to be padded to whatever maximum length you want them to be.
But doesn't encode plus do all of that for us?
Does the what?
Doesn't encode plus do all of that for us?
It might. Have you used this before?
Oh, no, because that's in the notebook, right? There's an encode plus thing that he shows in the demo. So I don't understand what's the reason we need pipeline if encode plus does all of the things that you've just spoken about.
Well, I'm not sure, but I mean, this is basically an automatic. This is basically an automatic thing that has everything under the hood, and you don't see what's going on. So I'm imagining that it does all that under the hood, and you don't see it. Because all you have to do is give the classifier this input.
Sorry, Joseph, one thing. I'm not familiar with Hugging Face. What exactly is that? Is it just like a library of transformers?
Yes, exactly. So let's go to the, I guess, let's see, this is just a quick tour, but probably the opening page is better. Let's see. And now I don't know how to get back to, oh, there it is. So you can see that it has this tremendous library of models that involve BERT. And all the different flavors of BERT, and it even has a library that can be that's being added to all the time by the community. So let's see, I'm trying to get to the main page. I think this is the main page, yeah. But maybe, yeah, I think that was the page we wanted. This is the entry page. And I think transformers is what we want. Yeah, so this is, oops, that's not what I want. Going back, Hugging Face, I'm gonna go. So this is the transformer, this is the Hugging Face transformers page. So this is the first page you'll see. And it's basically a library of transformer models, and it has both TensorFlow and PyTorch versions. Hold on for a second. I'm going to close my window. There. I hope that cut down the noise a little bit. Yeah.
Yep.
Yeah. We have yard work every Saturday morning across the street from us. So yeah, so it's just got this tremendous variety of models. And as I said, they can be used in TensorFlow or PyTorch. So yeah, so all I did was went to the getting started. Let's see, a quick tour. That's what I went to. And so I just went through all of this. So now it's showing you what goes on under the hood a little bit. And you have these two things that you used. You have this auto tokenizer and you have an auto model for sequence classification class. And you just have to tell it what you want, in terms of the model, and it gets the tokenizer. So there's always, when you use Hugging Face, you always have to have a tokenizer and a model. So here's the tokenizer. You give it a sentence, and then it gives you an output. And I think this is the CLS. I'm not sure. I think this is the CLS token, and I think this is the SEP token at the end of the sentence. And then the attention mask is also, you also have to have an attention mask when you use BERT. And that's because of the way BERT was trained. It was trained with an attention mask. And all the attention mask is it has 1 if it's an ordinary token, and 0 if it's a padded token. So all of these tokens are ordinary. Even CLS and SEP count for ordinary tokens. And in this case, there's no padding. But if you had padding and you looked at the mask, there would be zeros at the end because you'd have to use because you'd have to use padding tokens, and every time it sees a padding token, it translates that to 0 in the attention mask. So far we haven't seen any padding is automatically applied on the side expected by the model. Padding token, attention mask is also adapted to take the padding into account. Yeah, here's where you have the padding. So the last 3 tokens are padding tokens, and so in the attention mask there are zeros. So yeah, the padding token, the coding for the padding token is just 0. The encoding. All right. So the steps, the 2 steps are in using BERT are, first you have to pass your input you have to process your input by the tokenizer, and then the output of that gets sent directly into the model. So the asterisk PT batch, it basically says this is a dictionary, and that we see that let's see, the batch, this is the output, the batch output, PT batch, was produced by the tokenizer, and we see that it is a dictionary. So you can see it's going through the items, and it shows you that there's 2 items in the dictionary. One is the input, and the other one is the attention mask.
Joseph, do you know whether uh, different tokenizers can be used or with Hugging Face, or it says you can learn more about tokenizers? Do you know that?
Yeah, let's look at. I think they have several possible tokenizers. So pre-trained tokenizers. Well, pre-trained tokenizer class has many methods, but the one you need for pre-processing is call. I was under the impression that they had different tokenizers that you could choose from, but now I'm not seeing where that comes from.
I think each model has its own tokenizer type. Like they have BERT tokenizer and XLNet tokenizer. Like yeah, each architecture has its own tokenizer.
Yeah.
Yeah,
That's
because
right.
Word uses word piece and ExcelNet uses sentence piece and GPT uses something else. Yeah.
Yes, that's right. So when you tell it this is what I'm remembering from the what you said jogged my memory, because when you tell it which model you want, it already knows which tokenizer. That's all it needed, and the tokenizer. Uh, well, the tokenizer knows once you give it the model name, it knows which tokenizer to use, and as Gautam said, each model is paired with a tokenizer. So let's see. I okay, so this goes through and just tells you how to do how to prepare your data with tokenizers and with a model and a tokenizer. Um, you can also so the first example is just with the default model, which I think is the default model for classification is this thing, Distilbert based uncased fine-tuned, as is to English. Um, I guess Distilbert is a streamlined version of BERT where they eliminate neurons that aren't important in the they eliminate weights that aren't important in the model, and they get something much more compact that runs faster. And I think the problem that has been noted in the community is that BERT is great, but it's also slow. Not only slow for training, but slow for prediction as well. And so Distilbert helps with this. Yeah, so that's this getting started thing, which is useful. Um, I found that, so the main thing I wanted to do today, which I can't, is to go through this tutorial. We can still go through the tutorial, but I wasn't able to get the notebook to run, and that was a problem with a whole. I tried a whole bunch of different Colab notebooks, different blogs that had Colab notebooks suggested, and I found in almost every case that the Colab notebook crashed. So, especially the one. Remember the one we were intending to use last week, where it was linked to the Jay Alamar's tutorial. See the illustrate. So down at the bottom, he has a link to take BERT out for a spin, and trying this, I found that I couldn't get this one to work. So that's why I had to look for other ones. Um, so let's go back to this tutorial. So this one has a very long video, which I didn't listen to, but he has a notebook, and he goes through it in some detail to do a problem that I guess he did a problem in a previous blog where he imported some reviews from Google and a set of reviews from Google, and then built a classifier to classify them. So basically, these are the pieces of his notebook, and we can see that this is just a setup part. Then he imports. This is where he imports the data sets that he had put together, the Google Play Apps reviews data set that he put together in one of the previous blogs. So these are just lines that import that. Then he reads it in, looks at it. So you see, there's a username, there's a image, and the content. I guess the content is what they're interested in, and then their score. So there's 15,746 of them, and there's 11. I guess there's 11 columns in the data. Let's see, column using. Oh, this gives a list of all of the columns, but I think the main thing we're interested in is the content. So the review scores are not balanced, but not terribly unbalanced, except for the middle score. So the scores go from 1 through 5. And so I guess he's gonna try to convert this he's going to convert this 5 classes into 3 classes. So, and I guess maybe that's by combining. I guess if you combine these two into one class and you combine these two in another class, then those three classes will all have roughly the same number of examples, and that's what he does. If rating is less than or equal to 2, that's the 0 class. If the rating is 3, that's the 1 class, and otherwise you return a 2 class. And now the data set is more balanced. Let's see. So then here's the pre-processing steps that we talked about. You have to add the special tokens to the SEP sentences, the SEP token at the end of every sentence, and the CLS token at the beginning of every review, of every separate review. You got to have padding because at the end, in the end, you have to have your sentences have to be of the same length. Then you have to create the attention mask. So these are the three things you have to do to pre-process. Let's see. So in his case, he's loading this pre-trained model called BERT base cased. And I think this is simpler. It's the one directly from the paper, from the original paper, and it's cased, meaning that it knows how to recognize upper and lower case. He says that the cased version works better in his case for the reason that all caps might mean something, might convey information. When you use when people use caps in reviews, they're conveying information that you would be ignoring if you did an uncased version. Let's see. So here's the tokenizer. It knows, for every model, it has its own tokenizer, as we said before. So, and this is what Gautam was pointing out. So, yeah. So, give it a piece of sample text. It breaks it up into tokens like this. Although I thought that that BERT is supposed to be using word piece. It's some kind of a subword level tokenizer. But this looks like just words.
Yeah, I had a similar question actually, and I was surprised by that. Does anyone have any idea why, given that you're using the BERT tokenizer, you're not going into the subword level?
So only if that word is not there in the vocabulary would it try to split it, right? It won't split every word into subword.
Oh, okay, so very simple words. These are all very
Yeah.
simple words, and so it's not having to do that. Okay.
Yep.
Okay.
So it happens in the vocabulary creation process. If a word occurs a lot in the corpus, it would just be added to the vocabulary. If it's slightly less frequent, then its subwords would be part of the vocabulary.
I see. So if you have like you might expect that compound words might be split apart, longer words. Okay, and so here's the special tokens that we talked about. The SEP token, which is at the end of every sentence, has the encoding of 102, and the CLS token, which is what it uses, what the BERT model uses for classification, all classification problems. That has to be put at the beginning of every bunch of every review of every sentence. It says at the end of each sentence. So, well, if you're doing I thought that a review could consist of multiple sentences. So, but I think you only need one CLS token at the beginning. I guess if you're just classifying single sentences, then there's one of these tokens at the beginning of every sentence. But if you're classifying a whole paragraph, which is like more likely what a review consists of, what a movie review consists of, then you would just use this token once at the beginning. And then, as we mentioned, there's a special token for padding, and it has the encoding of 0.
Is the length of the size of the vocab predetermined with the tokenizer? Or
that's a good. It
Yeah,
must
it's
be
30,000 for BERT, I believe.
okay. That makes
That's
sense.
predefined.
Yeah.
so it's not variable because it's pre-trained.
Yep.
Yeah, so I guess, yeah, so it's not variable for the task. It only depends on the model that you've picked. Let's see. So okay, so oh, we also have an unknown classifier. Okay, and this is what John was saying, is that you can use this method to do all those pre-processing steps. So you can set it to pad to max length, and max length is what you can set the max length, and then you can pad to max length. I think there's a limit on this. I think it's 512 with BERT. The longest sentences you can have are 512 tokens. Let's see. So here's the method to add the special tokens, the CLS and the SEP tokens that we talked about. You don't need that. Pad to max length means that it'll add those mask tokens, those padding tokens that you need. And then it returns the attention mask because you need that. And return tensors equals PT means that it'll return PyTorch tensors. And I forget what it is when you want TensorFlow, but there's another, I think you just put true, and it'll return TensorFlow tensors, because you need that to go into the, as the input into the model has to be in tensors. Let's see. Okay, so the token IDs are now stored in a tensor and padded to length 32. And you can see them. There's the CLS token right there, the SEP token right there that marks the end of the sentence, and then the padding tokens that mark the rest of it. And there's the attention mask, and as you can see, it has ones wherever there are normal tokens and zeros wherever there are padding tokens. So there should be, each one of these padding tokens would correspond to one of these zeros in the attention mask. Okay, so now you can look at, let's see, I guess you can look at the tokens converted back into the words. And there's the original sentence with the CLS token and the SEP token at the beginning and end, and padding tokens for all the rest. BERT works with fixed length sequences. So max length in BERT is 512. So what is this doing? This is plotting a probability distribution of the token count in each of the inputs.
Length,
so
yeah, the length of each of the tokens.
Yeah, the lengths of each of the individual reviews, I guess, in tokens.
Yeah.
Okay. So that's what we're seeing. And so the max is somewhere around 20 or something, 10 or 20 words, which makes sense for a sentence. And I guess you know that when people write reviews, they don't often punctuate, so they may not put periods in things. So they might just run on in a stream of consciousness sort of way. And so some of the reviews actually have up to 200 tokens in them. So they chose a maximum length of 160. That puts them somewhere around here. And I guess they're cutting off the reviews that are longer. Okay, so now creating a PyTorch data set. They create their own class to do that. Let's see. This seems to be doing all the things that the encoding. Oh, okay, so this is calling the encoder, just as we did before. And then it returns the review text, it returns the encoding of the review text, and it returns the attention mask, and it returns the target, which would be the labels. I guess you have to have labels for this task. So since it's labeling the sentences. So I guess this is how to create the data set. Let's see all the pieces if we understand them. The reviews are the reviews, the targets are the targets. The tokenizer is the tokenizer that you've imported. The max length is what they said was going to be 160. You need a method to return the length of the review, so that's this. Get item review equals string, so reviews item. So this converts the review to a string, and then this gets the target for that item. Self.reviews.item. Why wouldn't it already be a string? I'm not sure. But anyway, so then it calls the encode method, the encode plus method, which we've already seen, and it gives it the review as the input, the review as converted to a string, I guess. Add special tokens for the CLS and SEP tokens. Sets the max length. Now I'm not sure. There's two different max lengths that they talked about. One is, I think they said 32 up above, and now they say 160. So I'm not sure. I guess there's only one. I guess now that you've said that you want 160 for the max length, that gets passed to the tokenizer as well. Yeah. Return token type IDs. They didn't use this. The previous time we saw this, encode plus called it, they also had false. I'm not sure what this does. The return token type ID is pad to max length. We want to do that. Return the attention mask, and we will return the tensors in PyTorch format. Okay, and then return. So this is a, let's see. This is one of those classes that actually, oh, okay, it returns these items. I guess I was thinking that it was one of those classes that is a function, but that gets called as a function, but I don't think it is. So, okay, so you do the train test split method to split your data up. Test size 0.1, so 10% test, set the random seed. Split it up again. Okay, so you're splitting your data set into train and test sets, and then the next thing you're doing is you're splitting the test set into validation and test set. So we've seen that before. Half of it, so 10% is the initial test set, but then you take that test set and split it up into half validation and half test. That's what this thing does. Okay, and then we can see here's the original set of reviews, and 10% of it is split into half and half into a validation set into a test set. Then he creates a data loader. I guess this is method we've seen in the FastAI2 library where you create data loaders, but I guess PyTorch has its own way of creating data loaders too. So data set, let's see, I'm sorry, I'm scrolling up here. This is where we created our data set. So that would be the input to the data loader. Let's see, tokenizer, max length batch size, TF. Let's see, reviews. I'm not sure. Okay, DF. I guess DF is the data frame that goes in. We haven't seen how DF gets made, but presumably DF. Oh, DF must just be the input reviews in a form of a data frame, because it has content, which is the reviews, and sentiment, which is the target classifications. Sorry?
It's the CSV file we inputted earlier.
The CSV file we inputted earlier. Let me just scroll up and see that. Yeah, the one that he created in the previous the one that he created in the previous the previous post before this one, which I didn't actually go through. But yeah, so that's when he loaded the CSV file, and okay, so that's where he's getting that from. Sorry, find out where we are. Oh, here's the one where you create data loader. So it returns a data loader object which takes as its input the data set that we created, the batch size that we specify, and I guess, the number of CPUs that you want to use in processing it. You need a batch size. And okay, so having that as a helper function, you create a train data loader, a validation data loader, and a test data loader from those three sets, giving it the maximum length and the batch size as inputs. Data next. Okay, so now it just shows you what one of those, well, so this is how you would use the data loader. You do next iter, and it will give you back a batch. So looking at the keys, and it would have a review text, input IDs, attention mask, and targets. Not sure what the input IDs are, but we know what the review text is. The review, the attention mask is the attention mask that we created, and the targets is the label for that batch, for those reviews. Let's see. Attention mask. Okay, and just looking at the size of those torch tensors that come out, input IDs. So there's the batch size is 16. The 160 is the length, the max length. So the input IDs, the attention mask, and the targets. The batch size is 16, so you need 16 targets, but each batch has 160 tokens in it. Okay. So I guess this is where the Colab notebooks starts. Let's see. BERT for sequence classification. So I think we're just using BERT for sequence classification for this one. Oh no, he's using the basic BERT model. We've already seen that. The BERT, the uncased BERT basic model. So pre-trained model name, we already have that. Coding sample text. BERT model input IDs and coding. So I'm not familiar with this structure. You get the BERT model from pre-trained, but you put the input IDs. Oh, and we already created the input IDs, the input vectors. So you encode them. You encode the attention mask. So I'm not sure what these things are doing. I'm not sure why we can't just put in I thought the input IDs were already encoded, and I thought the attention mask was already encoded. But I'm not sure why we have to do this again here. Does anybody have any insight about that?
I think if you just taken the input IDs, then they're missing the CLS at the start and the separator at the end. So I think that's all that's doing.
But I thought we put them in. I thought when we built those, we told it back up here.
You have the batch of tokens that you have built, but you need to pass that through the model to get the last hidden state, right? So isn't that what it's doing, is getting you, after it goes through the BERT model, then the output which it gives are the two things on the left. I forget, you'll have to go down.
Yeah, go back down
so you
here.
can look at it.
Yeah. Last hidden state pooled output. Right.
Yeah, so wouldn't you have to put your tokens and the attention mask through the BERT model in order to get to the bidirectional encoding? All you have done is tokenized, right?
Mm-hmm.
So you have to put the token through the model in order to get to the last hidden state and whatever the pooled output happens to be. I don't know what that is, but you'd have to send the tokens and the attention mask through the model to get to its.
Okay, that makes sense, right? You need to have we already know that BERT needs those two inputs. It needs the tokens and it needs the attention mask. But I guess the the problem I have is I thought we already tokenized everything. That's what we were doing above, in the steps above. So why do we have to encode everything again? I don't
Joseph,
understand.
that's just a dictionary. It looks like a dictionary. He's just getting the input IDs out of that dictionary. Encoding looks like, I mean, he's just keying. He's not passing input
I
IDs to
see.
the encoder.
I
Yeah.
see. That's good. Okay, so encoding is something we already built. Um, let's see. Let's go above and see where we did that. So I mean, Srinivas's point is that you need those two inputs. The model has to have the input tensors and the attention mask. And Gautam's point is that you're getting those out of this dictionary called encoding that you built somewhere above. Yeah, so that makes sense. Let's just go refresh our memories about where we built that dictionary.
That
Right
encoding
here,
would be the input to the model. I
encoding.
mean, yeah. I don't know why he calls it encoding, but yeah.
Well, here again, the input IDs are the dictionary that's being returned is input IDs, which is the encoding of input IDs. So, and the attention mask that it returns is the encoding of attention mask. So I'm not quite understanding what that method encode is doing. Well, as you're saying, Gautam, it's not a method. It's basically a dictionary, and you're just getting at those elements of the dictionary. I think that makes sense.
Yeah, I think in this particular instance, he's just showing uh, a single like how the model would act on a single example. So he's just passing encoding of input IDs to the BERT model and encoding attention IDs to the BERT model and getting the output.
Okay, that's good enough. Let's move on. Um, back. Where were we? Oh, now I'm lost. Go back up to where? Yeah, here we are. So here's running the BERT model. Last hidden state is the sequence of hidden states, and I think it's only the first one that we really need for our classification task. Last hidden state shape 132,768. The hidden states in BERT are size 768, so that's where that comes from, and our batch size is 32. I thought. I don't know if it changed from 16 to 32 somewhere, but anyway, I'm assuming that batch size is 32.
No, he talks about 32 tokens.
32 tokens, but
Not
isn't
batch.
that's not a batch size? Okay, it's the length of the input example, I guess.
Yeah.
We know that the hidden size in BERT is 768, so that's why this is that. That's why the size is 768. Pooled output is a summary of the content. It's also 768, but it's only one summary of the content. So it must be some kind of concatenation, or no, some kind of adding or averaging of all of the 32 outputs, the hidden states for all the tokens in our batch. So it only has a size of one. Well, a size of one unit of 768. The length is 768 because that's the hidden vectors, and the hidden vectors in BERT are length 768. So this pooled output is in some way it's combining all of the I think it's combining all of the hidden vectors in one, maybe by averaging or summing, something like that. And I don't know why they have to use that in the classifier model, because I thought that the classifier only needed the very first hidden output, the very first hidden state that corresponds to the CLS token.
Joseph, I think that's what they are talking about in this case. Pooled output might be the same CLS token uh, embedding. I mean, the final embedding of the CLS token. It could be the
Okay,
same thing.
could be. Although I would have thought that it would be the well, let's see. I would have thought that it would be the first element in this 32 is the CLS token. I mean, the first element in this
Yeah.
32 length thing corresponds to the CLS token, and I would have thought that that's the only thing that the BERT classifier needs.
And they could be the same, right? They might be just
Could be the
giving it
same.
in a convenient way.
Could
order
be
to
the
get
same.
a
Yeah.
true result, you have to do something to all the tokens.
Yeah. Either add them or average them, something like that, or take their max or something like that. Um, it's some kind of aggregating function on these 32 tokens that combines them all to produce one. Sorry, 32 vectors, and it combines them all to produce one. So that's the pooled output.
In terms of that pooled output, what is that giving you from the BERT model?
It's giving, sorry, it's from the input, it's giving you some kind of a summary of the content by averaging over or summing over or taking the max of these 32 vectors. It's giving you some kind of something that has combined information from all of the tokens. Does that make sense?
Yeah. Okay. Is there a quick way to look at what does the pooled output? If you click on it, does it lead you somewhere, Joseph? Or
No, unfortunately it doesn't.
okay.
Although we could do a search. Let's see. This doesn't have really an answer. I think some.
No, never mind. We can look it up offline.
Well, here's another one. Why the pooled output just uses first token to represent the whole sentence. That's what we were thinking, right? That's what Gautam was thinking, that it's just going to use the. Anyway, yeah, we can look that up. There's one on Reddit. Anyway, yeah. So there's something going on with the pooled output that, in some way, summarizes the set of tokens that you gave it for input. Let's see, where were we? Sorry. Yeah, there we were. Between hidden state, attention, pooled output is a summary of the content. Okay. Use all of this knowledge to create a classifier that uses the BERT model. So then they built a class to do that. It's a super class of sentiment classifier. So apparently there's already something in Hugging Face that knows what a sentiment classifier is. Self.BERT. This gives you the specific model name as an input. In this case, he was using the BERT uncased basic model. You can put dropout. You can, I guess the output is going to have to be some kind of a, I guess the output is going to have to be some kind of a classifier that takes the outputs and converts them to zeros or ones, or in this case, 0, 1, or 2. N classes is 3, so that's going to, this is going to create that last layer that you need to take the BERT outputs and transform them to numbers between 0 and 2. Let's see. So it's got a forward method. Let's see, that needs input IDs and attention mask. Okay, pooled output. Okay, so self.BERT Input IDs, attention mask. Oh, there it is, self.BERT. So self.BERT is the BERT model that you're using. And so the forward method is just to get the pooled output from BERT. So now I guess they don't care about the hidden, all the hidden states. They just want the pooled output. So maybe what Gautam is saying is correct, is that the pooled output is the first token.
I just sent a citation from Hugging Face documentation about this pooled output, and okay. It's the output which corresponds to this first token, but processed by linear layer and TON-H activation function. So it's this output of the first token and further processed with linear layer and activation.
So yeah, so this is great. I'm trying to understand what this means. The last hidden layer, the last hidden state of the first token of the sequence is further processed. So this is the definition of the pooled output, right? The last layer hidden state of the first token. Yeah, that's what I thought it would be, because that has all the classification information in it. The last hidden state of the first, from the last layer, you take the hidden state of the first token, and that should be the output from the CLS input. Further process, but now you're saying that's further processed by a linear layer and a TANH activation function.
Yeah, that's what is used in original pre-training for next sentence prediction task. So it's not exactly a sentence embedding, but like this output pre-trained to predict whether it is next sentence or not.
I see. But that's not the task we're doing in this case. We're not doing. Yeah. I don't see how the next sentence classification, the next sentence answer is going to help us with classification, though.
Isn't it pooled output as opposed to pooler output?
Yeah, that's was my question. Is it pooled versus pooler? Are they the same or different?
Yeah. Pooled output.
Yeah, so what I think about this, so in original pre-training, this output is meant to encode information about all the sequence BERT processed, because we need to predict whether those sentences are next to each other or not. So it needs to like compress this information about all the input, but that's why it's good for this classification task. We need to fine tune it, but actually it's already kind of sort of serves a similar goal.
But I think that what they end up doing is we don't need this linear layer and the TANH activation function that gives you the this from the next sentence prediction. I don't think we need that last layer. All we need is the last layer hidden state of the first token. And I don't think we need to do that further processing. We just need to take that last hidden state and then put that through a linear layer. And I think that's what they're doing here. They're putting it through a linear layer that maps it to the three-state target, that maps it to the 0, 1, or 2. That's what I think, but it would be good to know what this pooled output is, because that's what they're using. So let's see. Put self. So this is this. Yeah. So as we can see, it's pooled output that we're using from the model. And it's, I guess what Srinivas pointed out is that pooler output may not be the same thing as pooled output. So it'd be good to figure out what this is, but
yes,
what
it is the same. We can look at the documentation so everybody can see and and discuss it. It's in Hugging Face BERT model forward method.
Okay. So can you put a link to that on the chat and we can go there? Oh, thank you. Okay.
So,
oops, I didn't want to do that.
While you go there, Joseph, so what the person was pointing out may be that he may, that BERT model has a built-in classifier which it uses to predict the next sentence. And
Yes.
in this case, as he's saying, we use that ability, but fine tune it to predict the sentiment. Because for both of them, his point, I think, is valid, which is for both tasks, what you are after is trying to get from all the tokens in your sentence an indication of, it could be A or B, an indication of whether the next sentence is an actual follow-on sentence or not, which is what BERT actually does during its training. And in this case, that's fine-tuned by using that output, but fine-tuning it to actually predict whether it's one of the three classes.
I understand that idea, but in other words, you map the 0 or 1 by some means to a 0, 1, or 2, right? Because that sentence classification task, the output is just 0 or 1. With 0, it is similar to the sentence, or 1, it's not. But why do we need that when we can just take the hidden state itself and map that to the?
But
in other words,
just the hidden state is of one token, right? Whereas you have to summarize the tokens to decide, because you have, for example, in the example you showed, there are 32 tokens.
Yes.
And right, so each token would have, or it's, and you need to combine those tokens, right? That's why you need to pool.
Yeah, but if you take the pool, okay, so what if you just take the pool, which is a vector of length 768? That's what I would think. You now map that directly to 0, 1, or 2 for our classification task. Why do you have to put it through the linear layer that maps it to a 0 or 1 first?
Yeah, that, I mean, and it may just be that that's actually it's linear plus dropout or whatever that they have. Yeah, so that may be the default thing they do that they've found works best for classification.
Yeah, so, okay, so if what Arto is saying is the way they do it, then you're mapping 0 or 1 to 0. You construct another linear layer on top of the Tanch layer that maps the output of the Tanch layer, which is 0 or 1. It maps that to a 0, 1, or 2. Is that what you're saying, Arto?
Yeah, but there are 768 0, 1. That's not actually 0, 1. That's between 0 and 1, and there are 768 of those numbers. So that's a vector of 768 numbers.
Yeah, but there aren't 768 sentences. There's only one sentence, and so there should only be one label.
The hidden
right,
dimensions.
But that output is 768 dimensional.
Yes, but the Tanch output is 0 or 1.
Yeah, that's 768 0 or 1s.
Okay,
Joseph,
so
it
you're
doesn't
saying that,
matter anyway because sorry, we are fine tuning it to our task. And even if you were to just take the first hidden state, you would still add another linear layer on top of it, because that is what the model does in the block that you are describing. Even then you would still add a linear layer on top of it, and you are training that. So it doesn't
yes,
really matter if you just take pooled output or hidden state, because you would still add a linear layer on top of that and train it on our task. So it doesn't matter too
right,
much at the end.
right.
Yeah,
Okay, so
that's the
you're saying
idea.
that as long as you have a 768 pre-trained input, which you get from pooling, and it could either be from the first from the first from the output corresponding to the CLS token, that's 768, or
Hmm.
the pooled output, which, as Arto is saying, is 768 zeros or ones that are processed by that Tanch layer. In either case, it's that output is 761, and then you have
Yeah,
to build another layer on top of it
yeah.
to do the classification to
So you
0,
have the
1, or 2.
freedom to add whatever neural net you want on top of that 768. So yeah.
Yes,
Yeah,
yes.
so it's a question of where you tap into the original BERT network to customize, and that's something which is definitely important to figure out. But I guess what we are debating is where we are tapping into the
Yeah,
output of the original BERT to then convert or fine tune it to what we want.
Uh,
yeah.
yes.
Both could be tried out, and yeah.
Yeah.
Yeah. Okay, so with that understanding, let's go back and see where things go from here. This is the one. Yeah. So sentiment classifier. So it builds that extra layer, and it builds that extra layer, which is done here, the linear layer that maps the hidden size, which is a 768, to the three classes. And I guess, as Srinivas mentioned, you put dropout in there to help with the training. Let's see, forward. So here's forward, and the output is self.drop of pooled output. So pooled output. Okay, so you get this pooled output. Um, then self.output.
You apply dropout on the pulled output and then pass it through the linear layer.
Okay, I see that part. I see the part where you apply dropout right here, but then yes, that's right. And then here's where so it's exactly what you said. Then you pass that output through self.out. So and that's this output. So self.drop pooled output. Pooled output. Self.bert. Oh, so self.out, this is that last layer that we were talking about, that gives us our class out as the output. It takes the 768 length vector and makes it into maps it to 0, 1, or 2. Yeah, yeah. So that makes sense. That's what this sentiment classifier is doing. All right. We already saw that BERT is doing all the work. We use a dropout layer for some regularization and a fully connected layer for our output. We just saw that. Note that we're returning the raw output of the last layer, since that is required for the cross entropy loss function to work. Raw output. So the raw output means that there's no sigmoid, there's no activation function on top of it. It's just the linear layer, right? So sentiment. So now they're instantiating that sentiment classifier. Nope. Yeah. Instantiating the sentiment classifier, putting it on GPU, I guess. Input. No. Does anybody know what this to device means? Because I think the next step is when they put it on.
I think it is to GPU.
Put the
Yeah, put the
model on.
model on the
Put the
GPU.
model on GPU, right? And now you put the data on GPU as well, and the attention mask. So those are the three pieces that you need. And now I keep seeing this 16. I know 16 was the batch size. I'm not sure why the previous thing said 32.
32 tokens, Joseph.
32 tokens.
For that particular example.
For that particular, so that is one, oh, 32 tokens in that review. Is that it? And then we
Yes.
have 6, and then a batch is 16 of those, but they don't have to be all 32 tokens, I guess.
Yeah,
They're all up to 6,
max
up to
length, right?
max
So,
length of 160.
yeah.
Okay, so that particular review was 32, and as we saw, the distribution of reviews sizes was peaking somewhere around 10 or 20 tokens, so that makes sense. 32 tokens would be sort of an average, not too far away from the average review. Okay, okay, so now comes the last step where we take the raw output from the linear layer and apply an activation function on, or a softmax function on top. Instead of the, sigmoid, if we were doing 2 classes, we would want a sigmoid function, but we're doing multi-classes, so that's why we need the softmax activation. So softmax, we already have F. I guess F in PyTorch is, you can access the softmax function from it. And why are we, oh, and okay, and so here's the 16 items in the batch. That's these, and then each item gets 3 outputs, which are probabilities. And then to classify, you just take the max, which one had the max. I guess that's it. So reproduce the training feature procedure from BERT. Okay, so now he's okay. I'm not sure what he's doing. Sorry.
Is fine-tuning the layer, as Gautam pointed out, right? We have to train that linear layer and stuff. I mean, BERT will produce the output until you get to the pooled output, but the rest of it we have to fine-tune and train.
Right. But what is that? I thought we were doing something here. We were, I guess we were predicting with just the BERT model and not doing any fine tuning here, right?
No, I think that's the whole model, but he's just showing it without training. I think he has not
Without.
trained it yet, right? He's just showing a random example on untrained model.
Yeah, but doesn't this?
No, it's the whole model. It's not just BERT. It's the BERT plus the dropout and linear and all that.
Yeah.
Yes, yes. Right. But something has been processed all the way through BERT. That's where you get these numbers. So
No, not just BERT plus the linear, the whole model.
the whole thing that we built, right? So we already have these outputs. That means BERT's job is finished. It's actually made a predict. You can actually make predictions from these things.
But this is an untrained model, right? It's not fine-tuned yet.
Yeah. So this is just the outputs from the pre-trained BERT model, and we've just accepted whatever was in the pre-trained BERT model. Is that's the
pre-trained BERT model and the untrained linear bit at the end.
Yep.
The untrained.
We just added a linear layer at the end, right? Which we haven't trained. So.
Right. That's right. We haven't done any training on the linear layer. That's a good point. So yeah. So this is all you get. But now we have to train it. So now he's using the Atom W. I'm not sure what Atom W optimizer is, other than that it's some variation of Atom. But that's what's used in Hugging Face. Corrects weight decay. So it's similar to the original paper. And I guess I remember that Jeremy talked about this in his class once, where there was the original Atom got something wrong, and they fixed it with Atom W.
Yeah, because of, I don't exactly to your point, I think the original Atom was either double counting or it was doing weight decay and applying something to the loss, and they aren't exactly equal, blah blah blah. So Atom W was the corrected implementation of Atom with just the weight decay applied, if I recall correctly.
Okay, so that makes sense. Linear scheduler with no warm-up steps. Linear schedule with warm-up. So linear, I'm not sure what linear schedule is. Is that ramping the learning rate linearly as you go through the batch, or? I'm not sure what that is.
Can someone remind me why we need what's the purpose of the scheduler? What does that do?
It changes the learning rate in a certain way that they find to be effective. Remember that Leslie Smith's paper where he found and Jeremy went through this, where you ramp up the learning rate initially to a high value and then you back off. And
okay, yeah, thanks.
Yeah, so in this case, I think it's just a linear ramp. You're just ramping it up in some linear way, but that somebody has already found works well or something. No warm-up steps, blah, 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 with warm-up. Okay, number of training steps equals total steps, so fx equals 10. I don't know where total steps is specified. Oh, total steps right here, length of training. So it's just the length of the data loader, which is 16 batches, times the number of epochs. No, the length of the data loader is all of the batches. Right?
Yeah, it's the length of the batches in the data set.
Length of the
It
data
will
loader.
be the data set size divided by batch size.
Yes. The length. That's what this gives you.
Yeah.
So the number of batches in the entire corpus that you're putting in, and then you multiply that by the number of epochs, because that means you're going through the whole thing, 10 times. So that makes sense. Total steps. And so it's doing some kind of a linear scheduling over this number of total steps. It's gradually increasing the learning rate in some way, or maybe gradually decreasing the learning rate in some way. I'm not sure. Okay, loss function, cross entropy loss. That makes sense because it's a multi-class problem, and they put that on the GPU as well. Okay, batch size 1630. Oh, how do we come up with all the hyperparameters? BERT authors have some recommendations. I guess this is from the original BERT paper. Small batch size is 16 or 32. Learning rate using Atom 5 times 10 to the minus, some multiple of 10 to the minus 5, small multiple of 10 to the minus 5. Number of epochs to use 2, 3, or 4. So he's going to ignore that because he wants to put 10 epochs through. Note that increasing the batch size reduces training time. But gives you lower accuracy. Not sure why that would be, why either of those things would be. I guess there's an overhead to processing each batch. Maybe that's it. Although I'm not sure why increasing the batch size gives you lower accuracy. Okay.
I read somewhere, I'm not sure if how true is it, but that like when you have a lower batch size, you have more noise in your gradient. So
yes.
It acts like regularization,
Yes, I think that is absolutely correct. But there must be some kind of a sweet spot where the batch size is just the right size. And if you go lower, then you have too much noise, too much regularization. And larger, I don't know why having large batch sizes would, well, here's how it works, I guess. If you have, the larger your batch size is, the more constrained you are to go towards the actual, in the direction of the optimum. But as Arto said, reducing the batch size introduces noise, and that means you'll take directions that are not necessarily towards the optimum. So that helps you to get out of local minimums. So I would guess that so that the two opposite poles are small batch sizes gives you a lot of variation, a lot of randomness in the directions that you go, and large batch sizes mean that you'll have a hard time getting out of local minimum because it's always going to push you towards the local minimum because it's a much more accurate direction. Does that make sense? And so there must be some kind of a sweet spot in between where the batch size is small but not too small, and large but not too large, if that makes sense. Any comment? Okay. So now he's going to write a helper function to train for one epoch, and then I guess they call this for all the epochs. So train epoch takes the model, the data loader, the loss function, the optimizer, a device, I guess that's the GPU, scheduler, we saw that learning rate scheduler, and number of examples. It's one epoch. So, and examples would be the total number of examples in the whole epoch. So, let's see, there are batches, and each batch has examples in it, and then there's a certain number of batches that makes up the whole epoch. So, it's the total number. It's the total number of examples in the epoch. We've seen this before in FastAI. There's always, there's always a model, and you have to have a data loader, and you have to have a loss function, and you have to have an optimizer. Those are the sort of the three things that every training process, well, four things that every training process has to have. So that makes all sense. That all makes sense. And then these are just the parameters. The device is the GPU, I guess. And then the learning rate scheduler, which is optional in FastAI. Yeah, so that all makes sense, the way this is built. So now you train. Let's see. Oh, so now you provide, let's see, model.train. We have train epoch here, and we had train up above, I think. Nope, I'm not sure where train. I wonder if he means train epoch model dot.
I think that's you're just telling that it's in the training phase of the model. It's supposed to be
It's
just
like a
model dot
switch.
train.
It's a switch. It's just like a switch to tell it that it's in the training phase.
Yep.
Oh, okay. Okay, that makes sense.
It's supposed to be just model dot train. It's not model equal to model dot train.
I see.
It's for the dropout. So that
Yeah, because if you just did that, that would set the switch inside the model, right?
Yep. Yep.
Okay. Okay. So then you start out by initializing losses and correct predictions. I guess this is a count of the correct predictions. And now you run. I guess you run this training now for D in data loader. Input IDs gets the. I guess it just gets the batch. There are three parts to the batch, right? There are the input. There are the input vectors. There's the attention mask, and there's the target. So those are the three things that you get out of the data loader. D in data loader input IDs. Outputs equals. Okay, so, but why does it? For D in data loader input IDs equals D of. I'm not sure. So you're processing the whole. You're processing the whole thing here. The data loader has everything in it.
But the data loader is an iterator, so you need to take each batch from it and shove it through the model, which is what he does.
Oh, that's right. The loop. I was thinking that the loop ends here, but let's see. I'm trying to find out where the matching parentheses for this one is.
Oh, that's just at the opening of the model. Outputs equal model, open bracket.
Oh yes, okay, right. So this is what I was confused. This thing is inside this loop. Okay, so
Yes.
each time it gets the inputs, the targets, and the attention. And I was thinking that this was, my eyes weren't lining it up. I was thinking that this was another line. So this is in the loop. It gets these three things. It puts them through the model. What is it doing with? Oh, it doesn't need to put the targets through the model. Well, it does actually. Outputs equals model of input IDs. What's it doing with the targets? Preds equals
Right below.
loss function outputs targets. Okay. Okay, so it gives the model its inputs, its input data set, and then it only needs the targets to compute the loss function. So that makes sense. And this is still inside. Let's see. We're still inside the train epoch function. Okay. So you get the torch.max of outputs. So the predictions are the max. Remember the outputs are those three-dimensional vectors, and it's averaging. It's taking the max over that vector. That's what the preds are. The preds are the predicted classes, which are going to be 0, 1, or 2. And let's see, loss function, outputs, targets. Yeah, so it needs to compute a loss. It needs to be able to compute a loss function from all of the examples that go in. And correct predictions, you increment it for, let's see, preds equals targets. So preds is going to be a whole, I guess it's going to be a whole batch, right? Because let's see, is this still? Yeah, it's still inside this. I guess this loop goes all the way down. Sorry.
No, it stops at outputs. So at the end of the outputs equals model, that's where it stops. Yeah, it stops there.
I'm not sure. I think the rest of this is all inside of this 4D and data loader loop.
You're right. Apologies.
The whole thing, yeah.
I'm starting to see it. You're right.
Yeah. Okay.
You have to
So
back propagate inside the, for each batch, right?
Yeah. Whole
yeah.
thing is inside.
Yeah. Okay. So then you get the outputs, you get the predictions, you get the loss function, you increment.
Yeah, unfortunately, he's going back and forth. I wish he had stuck all the loss code together. So he takes the preds, then the loss, then corrects the prediction, then goes back to appending the loss. So
yeah, this could be refactored a little bit to make it more intuitive what's going on. But yeah. So let's see, outputs, model, predictions, loss function, correct predictions. Okay, so this correct predictions is going to be adding how many of the batch it's going to be incrementing by how many of the batch got correct predictions, I think. Is that, D is a batch, right? For D in data loader. D is a batch, right?
Yep.
Okay, so then it's going to add how many of these 16 items were predicted correctly, and that's going to increment the correct predictions. Because correct predictions was initialized at 0. So it's going to tell you how many of the 16 were correctly classified. It's going to, where's the item? It's appending item, loss.item. Okay, so this loss function gets all of the,
Just that the outputs and the targets for the batch. So
yeah, so losses, so is the loss going to be for each batch then?
Yes, and
okay.
then losses is a list that he keeps and appends the loss.
losses got initialized to 0, so each to nothing, to empty. So this loss is going to be just throughout this batch, right? It's going to, sorry, as it processes through these batches, it's going to append one value for every batch to this list.
And then presumably we'll plot it later to see how it's doing, right?
Yeah, yeah. Loss dot backwards. So here's the back propagation. And then you're doing gradient clipping. Max norm.
Can you remind me what gradient clipping is?
Gradient, and then utils, clip grad norm. So gradient clipping was where they would prevent the gradient from exceeding some value, so that if it got up to some value, then, and I think in this case the max norm is 1. So whenever the gradient gets bigger than 1, it gets replaced with 1. That's what clipping does. And I guess the same in the other direction. If it goes to -1, it gets replaced with, if it goes lower than -1, then it gets replaced with -1. And
so is that like what's that? That's like regularization, where you're trying to ensure it doesn't get out of the way, or is it something else?
Yeah, it's to avoid the exploding gradients problem. Let's see if we can look this up really quickly. There it is in PyTorch. Clip gradient norm of an iterable of parameters. Okay, norm is computed over all the gradients together. Gradients are modified in place. Okay, so I guess the norm is computed over all the gradients together, and that must mean for the batch. Parameters, max norm is the max norm of the gradients. So it gives a very brief explanation. It just clips the gradient norm, and that's what clips means. It means that it doesn't allow the value to get outside of a bound, right? If the thing gets bigger than 1, then it sets it to 1 so that it doesn't saturate. Sorry, so that it doesn't increase without bound. Does that make sense?
It does. It does, but why would we use this versus something like a regularization technique?
I'm not sure if you call it a regularization technique. Maybe you would. I guess they found that if they didn't use this clipping method, that the norms could get, that the gradients could, you get the exploding gradient problem. That's what I'm guessing. That's why they found they had to do that.
And it's using the L2 norm as default.
L norm type equals 2, yeah, L2 norm. So I'm thinking that this means the norm is computed over all gradients together as if they were concatenated into a single vector. All gradients together. So you can imagine, yeah.
Sorry, the difference in clip grad norm is it modifies all the gradients, whereas the normal clipping just cuts down the single large gradient. So in this one, it would ensure that the norm of the gradient vector as a whole does not exceed 1. So all of them get adjusted so as to not exceed the L2 norm limit.
Okay, that's an insight. That's great. I think that's so.
But for the batch or for everything, because you're working at a batch level at the moment.
Yeah,
right?
for the batch. I think it's the batch.
It's not bad. I mean, it's just suppose your model has 1,000,000 parameters, so you have a vector which is of size 1,000,000. I mean, doesn't matter if it's batch or anything, right? It's just gradients of your loss. The loss is calculated for the batch. Yes, it's just the gradient of the loss with respect to all your parameters.
But the gradient of the loss is calculated for a single batch, right?
Yes, the loss is calculated for that batch. Yeah.
Okay. So now we have all of these parameters, all of these parameters that are involved in the gradients. And we're making sure, as Gautam is telling us, we're making sure that we're adjusting all the gradients. We're not just clipping the high gradients, right? We're adjusting all the gradients by scaling them so that the norm is 1. Is that fair to say?
Yep.
They're scaling the gradients, multiplying it by some kind of a scale factor, so that the norm of all the gradients is exactly 1. So that sounds like a regularization. It sounds like some kind of regularization.
Yeah, in this case, L2 norm.
L2 norm of 1, right?
Yeah.
Isn't that batch norm? Or well, that's not the same as batch norm, is it? That's interesting. I haven't seen this before, but that's interesting. So they're keeping the gradient and making the gradient always 1. That makes sense in some way, because that way the learning rate exactly controls what. That way the learning rate is what controls the updates.
They aren't keeping the gradients to be 1, right? They're just ensuring that the L2 norm of all of the gradients for a batch is guaranteed to be less than 1.
Was guaranteed to be 1, I think.
I think it's less than 1, max norm.
Yeah, less
norm.
than 1. I thought it's cut off if it's more than that, right? And it becomes 1 then.
Yeah.
So you're thinking that if you get a batch that has a gradient of less than 1, then it'll leave that alone?
Yeah. Okay, but that's what I infer from the clipping bit.
Yeah, that does make sense. That's what the word clipping usually means. Means that you leave something alone if it's less than the limit.
I mean, otherwise you would have to artificially increase the gradients, right? To make it 1.
Yeah. Yeah, but what would be wrong with that if they're all increased in the same way? I don't know. Anyway, so that's interesting, and I think with Gautam's help and everybody's help, we understand what it does. We're not quite sure though why it does that, but probably has something to do with exploding gradients, with preventing exploding gradients. Okay, let's go back. Any other questions on this? I'm not sure exactly why it's being done, but
yeah, it is exploding gradients.
Is that right? Just to prevent the gradients from exploding. Okay. Back to this one. Yeah. Okay. So here we are. Clips the clip grad norm. Do a step. Scheduler.step. I'm not sure what's going on here. So we understand what this is doing. It's taking a step that's calculated by the by backpropagation. But what is this doing? Scheduler.step. Oh, increase the increment the learning rate for the next batch. I guess that's it.
Yes.
And then zero out the gradients for the next batch as well. So that's these 2 steps prepare for the next batch. And it returns. So it returns correct predictions over the number of examples, and it returns the mean of the losses for each batch. Number of examples. N examples.
All the batches, right?
Yeah, n examples is a constant, which is the number of examples in the entire training set. So it returns the correct predictions as a fraction of the entire training set, I guess. And then it returns the mean of the losses for this batch.
It's for the whole epoch, the whole data set.
Yeah, so that's the accuracy and the loss then, average accuracy and loss, I guess, that you're returning. Isn't it?
Hold on though, but correct predictions dot total. So this return is at the end of a batch, right?
You can't have return at the end of a loop,
right? At the end of
right?
the function.
return is at the end of the function.
That's right, because D is going through all the batches in the data. All right, so this is at the end of the function. So now it's finished with all the batches, and correct predictions over number of examples is the accuracy, right? And this is the loss. So that makes sense. Let's see, training the model looks familiar except for two things. The scheduler gets called every time a batch is fed to the model. We're avoiding exploding gradients by clipping the gradients using clip-grad norm. Okay, so that makes sense. Okay, now let's write another one that helps us to evaluate the model on a given data loader. Okay, so now we've got.
I think this time it's model evaluation or testing it rather than training.
Yes, no training. We're just taking the trained model and evaluating the result. Torch no grad. So that's what this does, I guess, to make sure that we don't do any backpropagation. For D in data loader, same as before. Outputs equals model of inputs. This is all as before. Predictions, loss. So this accumulating the correct predictions and appending the loss. So you can see that everything is the same except for this part, which is the backpropagation piece. I think other than that, it looks the same. Is that right? For DN loader inputs, sorry, I'm scrolling back and forth. Outputs, preds, loss, correct predictions. Yeah, everything. So this function here is exactly the same as this one, except it doesn't include the backpropagation step. Using these two functions, we write our training loop and we store the training history. So I guess here's the whole thing. For epoch in range, blah, 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 train epoch. Give it its input. Sorry, let me see. One of them is a val model and one of them is train epoch, right? So we're using the first function. For each epoch in range of epochs, we call that train epoch function that we just went through. We print the result. Remember, it just gives you all it does is gives you a loss and an accuracy. So you print the result each time. Then you evaluate it and print the validation loss and accuracy. So that makes sense. And then you append the accuracies and the losses and the validation accuracy and the validation loss into these lists. And then you go through this whole history and you find and you save the best one. Best accuracy. If val ac is better than best accuracy, but where's best accuracy? Does it initialize that? Best accuracy equals 0. So it initializes best accuracy to 0, and it keeps the best accuracy. Well, it's say so. Is this? Sorry, I'm just going through here again. This is a whole loop over all the epochs, and for each epoch you're getting this output and epoch in range epochs. Sorry, I'm trying to see if these are all included in the loop, and I think. Torch save. Is it going to save the model every time it finds one, or is this after the loop is done? I have a hard time seeing. This is still inside the loop? Okay.
Yep. So for each, okay, go
on. Go ahead.
So for each epoch, if the current accuracy is better than the previous best accuracy, it saves that model and it changes the best accuracy value. So if in my next epoch I get an even better accuracy, I just save that model, and it's yeah, and I just update the best accuracy.
I guess the thing that threw me is why would it save the model because now it's going to have to update. If the next time it runs the model's better, it's going to have to save on an overwrite with the new model. So it seems like that could be, that's kind of weird that it would do that because it's wasting a lot of time saving models. But anyway, that makes sense. That's what it's
I think
doing.
some kind of early stopping
Yeah.
would be a better thing to do here. Like callbacks or something, I don't know.
Yeah, so like if you see the accuracy doesn't improve for several times in a row, then you just stop right there.
Yeah, and save the model.
Yeah, that would make more sense. Okay, so now it goes through the 10 epochs, and we see how it trains.
Yeah, your early stopping point makes sense if he was doing something like 30 epochs, but since he's only doing 10.
Yeah, good point.
Yeah,
good point. Okay, so it's going to train, and then it takes half an hour to just do 10 epochs, or actually more than that, 43 minutes. And I'm not sure if he's training on a tensor processing unit or on a GPU. Anyway, so at the end, he has training loss, accuracy of 98% for training, and an accuracy of 89% for validation, which isn't terrible. So,
very random question. Can you use Colab's TPUs when using PyTorch, or is that only for TensorFlow?
that's a good question. I don't. Does anybody know the answer to that?
Yeah, you can use it. You can use it for anything.
Either one. Okay. I've tried. I mean, TPUs. If you don't have a Colab Plus, is that what it's called? A Colab Plus account?
Colab Pro.
Colab Pro. Yeah. If you don't have a Colab Pro account, you're not going to get a TPU. I think that's the way it works. You can wait, and maybe if you're lucky, you'll get one. But has anybody had a different experience where you can use ordinary Colab, the non-paid version, and actually get TPUs? Just short experiments that I've done have indicated that you can wait. You just wait, and you're not getting anywhere. So, yeah. Anyway, so he trains it for 43 minutes. He gets the best model seems to be 89, somewhere around 89% of validation accuracy. Somehow it seems unfair to take the best accuracy, because that could, I don't know.
No, you're just choosing the model which gives you the best validation accuracy, right? So it still has to, actually, since he separated the test, he would have to run it on the test and see what he gets to, which he hasn't done yet.
I think, oh, that's right. That's right. He's reserved the test set. I'm not sure he's going to do anything with it, but we'll see. Okay. Okay, so here's where we can plot the history that we saw. We recorded in that function. We recorded the history for each epoch, and so yeah, validation accuracy is kind of leveling off at 89%. The training accuracy starts to approach 100% after 10 epochs. You might try to fine-tune the parameters a bit more. What parameters do we have? We have dropout, we have batch size, and
learning rate.
The learning rate, yeah. I mean, but the learning rate seems to be pre-specified by that model, by that. Oh, that's right. Well, did we give that the learning schedule? Did we give that an input of any sort? Remember that he said that there were preferred learning rates that were pointed to by the original BERT paper that were sort of in the low 10 to the minus 5s. I'm not sure what that learning rate schedule takes, but maybe we could control that and change the learning rate, the initial learning rate in that schedule. Oops, I didn't want to do that. Okay. Okay. Oh, and then he said, if you don't want to wait 45 minutes, you can just download his model, which is kind of nice of him. Oh, and now he does go back to the test data. So yeah, you're right. He does go back. So now we use the eval. After we finish our training, we can go through and actually, if you wanted to, before doing this, you could go back and change some parameters and see if you can get a better result. Because it is the validation set, and so you're allowed to use it for hyperparameter tuning. And once you get some better parameters, as good as you want, you can then come, when you're done, when you're all done, then only then you come back to the test set and evaluate it. So 1% lower. So he had 89% for the validation, and he has 88% for the test, which is not too terrible. Now, why does he have to write this function? Get predictions. Oh, man. Okay, so here's a loop that does the back. Oh, it's just a prediction with torch no grad. So this is prediction loop, just like we saw before. Predictions. Similar for the evaluation function that we built above, except we're storing the text of the reviews and the predicted probabilities. So he's returning the texts, the predictions, which are the 0, 1, 2, and then the prediction probabilities, which are the 3 probabilities. And I'm not sure what real values is. Real values, there it is, torch stack, real values. Oh, so real values has to do with the targets. Oh, real values, I guess that's the true classifications. I was thinking it means something like real numbers or something, but no, it's the true classifications. Okay, so Y review, Y pred. So I guess once you've written this function, now you can just do the whole thing in one line to get all the predictions. Okay, then he runs the classification report, which gives you a precision recall F1 score and support, meaning how many examples were in each class. So as we saw before, well, let's see. Are these predicted classes or anyway? Calculates the accuracy, a macro average and a weighted average. We've seen this before, and I can't remember. It's this classification report from scikit-learn, I think. Macro average is, I think that's the accuracy of all 3 classes averaged together. So the average of the correct predictions on the negative, the neutral, and the positive. It's averaging all those together. But then the weighted average actually takes into account how many, what the support is. So it would give the negative average with a weight of 245, the neutral average with a weight of 254, the positive average with a weight of 289, and then it would divide that by the sum of all of those weights, which is 788. So, but in this case, the macro average and the weighted average are the same, it turns out. And then he says the neutrals are the hardest. They have the lowest recall and the lowest F1, which makes sense. I mean, the neutrals are the ones that are going to have some positive words and some negative words. So it makes sense that they would be the hardest to classify. Looking at the confusion matrix, you see that things look pretty good. 33 false wrong classifications in this for negatives, 38 for neutrals, and only 21 for positives. So now he's going over an example of one of the reviews. true sentiment, and neutral. So this is confusing. If you look at all these words, you can see why it comes out with neutral, because he's got some positive words. This is great. Price is too steep. That's probably going into the calculation. Sub-perfect score. That's probably going. So that's a negative sentiment. Worth 5 stars. That's a positive sentiment. So it's taking all of those into account, and it comes up with neutral. And it makes sense that it classified as neutral. I mean, a human being would probably say the same thing. This I don't understand, this graph. I've seen this. It's a bar plot, and it's saying that. Oh, it's saying for this classification, it says that it's very highly confident that it's neutral. It's not getting confused at all whether it's positive or negative. I guess that's what this means. So it's saying with almost 100% probability, I think this review is neutral, and it's got a little bit of confusion that it might be positive. So yeah, that's what this output is telling us, this bar plot. Yeah, so that's so then what's this last thing? Okay, so then he just makes up some review, predicted it, and it's obviously a positive review, and the classifier gets it right. So I think that was a pretty useful tutorial. And actually, when I ran this on Colab, several times it crashed and several times it worked. But I'll show you where it crashes. Sometimes it crashes near the beginning, and it says that it when you're trying to make when you're trying to do something with a data frame, it says that it doesn't know about pandas, so you have to tell it, you have to import pandas here, and then it works. Then down here when you're making graphs, sometimes it doesn't know seaborn, so you have to add a line importing seaborn, and then later on you need to tell it about matplotlib, again with another import statement. And I'm not sure, and sometimes when I run it, it doesn't have that problem. So I'm not sure. But then the main problem that I had was it didn't know where the data set was. Where was it? Okay, so I can load the tokenizer, I can do things, I can do all that pre-processing. But then this review, creating the data set, it crashed because
that's a PyTorch class that you need to import from utils. PyTorch or utils from PyTorch or utils import data set.
Is that right? Let's try that.
That's because you're using that as your parent class, right?
Yeah, but I thought that well, let's see. So you said from PyTorch.
It's torch. It's just torch from torch.utils. Yeah.
From torch.utils. Torch.utils. Import GP review. Import dataset.
Dataset. Yeah.
Okay, let's try that.
From torch.utils.data.
.data?
Yeah, .data.
Okay. Let's see if that works. Oh, that worked. Nope. Now it's. Oh, now you have to do this from. Is this a method from Torch or is it method from scikit-learn? Yeah.
scikit-learn.model selection.
So I must be missing some. I mean, this must be missing some cell where it does all of this imports and everything. Import train test split. df is not defined. df. I thought he had df somewhere. Oh well. So I think with those suggestions from you guys, I think you can debug this and get it to work. But sometimes when I run it, it actually worked without any without any change. So I'm not sure what's going on there. df. Why doesn't it know? df train df test. I think we already somewhere we had df. Well, anyway, I better stop because I know the Kaggle. I'm sorry, I took too long. Kaggle is coming right up. So thanks you all for